Hello, everybody, and welcome to your midterm review for your Earth Science class. This is Dr. Hurt, and we are going to be going over everything that's on your study guide and getting you ready to take your midterm exam. So buckle up and gird your loins and get ready, because it's going to be a slog through, about a 1 hour slog through this study guide. So first of all, before we even get into the material, I want to go over what we have to know, basics about the test, just very quickly. I know probably you know a lot of this stuff, but just going over it once again so there's no confusion. So this test is going to be worth a good amount, right? It's going to be worth about 100 and, let me get my correct pen out here. Whoops, there we go. Okay, it's going to be worth about 164 points, 80 questions. You have to take it, of course, in person. Hopefully that's not a surprise to you at this point, but you do have to take this in person, and you can take it either at OSO Campus Testing Center or the Heritage Campus Testing Center, either place. You can also take it with me. There will be a time for me to proctor you all, and that's kind of just walk-in basis. I usually do that in the evening time to give people that work a chance to come in and take the test after hours. Normal is 5 to 7 p.m., okay? So go to Canvas and check the announcements. I use this video multi-semesters, so it could depend what semester we're talking about. But anyway, Canvas will tell you the real time for that, okay? You should register as early as you can because slots are limited. They do fill up. So if you want to get a certain slot, let's say you want a Saturday, Saturdays fill up very quickly. So make sure you register early to get the slot that you want. Okay, you're going to have 6 days basically to take the test. It's a 1 week time period minus the Sunday, so it ends up being 6 days. Normal testing center hours are 8 a.m. to 4 p.m. Saturdays are a little bit different. I can't exactly remember the hours off the top of my head, but you should go to the testing center and call them to get that information. The place that you register for the exam is this link, so you can click that there and you can see where you register. There's also a video online that I probably posted for you all already showing you how to go through that registration process. It's not very hard. Okay, it's a closed book, closed note test, so it's a lot from memory. Okay, you're going to have to depend on your memory here. It will also have a mixture of different problem styles, open response. There'll be between 4 to 6 open response questions, and that means you have to type in an answer. It's usually just 1, 2, 3, 4 sentences, something like that. Those are worth 4 points each. There's matching, multiple choice, true, false, ordering sometimes, fill in the blank kind of things. So just be aware of that. There will be a couple ones where you have to put in a specific number. Like if there's a really specific number you might have to type in, like for example the tilt of the Earth, 23.5 degrees. That's the tilt of our axis relative to the ecliptic plane, right? So things like that you might have to type in as well. There might be some one-word answers you have to type in as well. And there'll be, in addition to that, the 4, 5, 6, I'm not exactly sure how many there are on there, open response questions that require more like a sentence or 2 or 3 sentences to answer. Okay, so you don't have anything to do during midterm week, so it's just to focus on the midterm. There will also be, like I said, a walk-in time for you to come in and take the exam. Normally I hold that at the Oso Creek campus computer lab, which is in STEM building 339. Sometimes if that's not available, I hold it at the Coles computer lab on Heritage Campus, Coles 302. Okay, Coles building 302 and that's at Heritage. Okay, all right. So that's kind of the basics of the test and the conditions under which you'll take the test. Let's go on and take a look at the material now. Okay, so first of all, we started off with philosophy of science. I have 2 questions. Oh, by the way, just another thing I wanted to explain about the test. Everything that you're going to see today on the midterm exam review is on the test question bank. Okay, so all this is on the test question bank. You will receive a random selection of these questions. Okay, so I can't guarantee you that this is going to be on the test or you're going to get that on the test. Okay, but it could be on the test. Okay, so but it all depends on what you personally get at the random selection from the question bank. Okay, so just make that clear. So anyway, philosophy of science. So there are 2 questions on the question bank from philosophy of science. You should make certain you understand all the criteria necessary for a question to be answerable by scientific inquiry. Remember, we had 3 things here. 1, 2, 3. It has to be reproducible. It has to be falsifiable. And it has to be something that's based in, the physical universe, right? It has to be physical, observable, something that you can sense and see. Remember that science, one of the things about science is it's empirical. Okay, it's based off of observation. So reproducible just means that other people have to be able to come after you've made your observations of your experiments or your observations. Other people have to be able to come along and reproduce your results, make the same observations that you made, make the same experiments and get the same results that you made, etc., etc. Okay, that's what reproducible means. Your observations can be viewed by anyone at all times. Okay, so that kind of produces problems if you're talking about something that's subjective, right? Other people can't come and view your subjective feelings and emotions, and that's why science doesn't really deal very much with a person's subjective, their feelings, their emotions, their things like that, right? Science deals with objective things that everybody can see and everybody can view and everybody can reproduce, all right? So another thing is that it has to be falsifiable. Falsifiable means that whatever your hypothesis is, it can be either proved true or proved false by evidence, okay? And evidence means observations, okay? Things that you can actually observe and all people can observe, right? It's reproducible, so all people can come and verify your evidence, all right? So falsifiable, things that are not falsifiable, for example, I had students, sometimes they'll say something like, invisible fairies that are undetectable come in the night and they, whatever mischief they do, well, it could be anything, but you can't verify invisible fairies that are undetectable with evidence, right? Because by definition they'd be undetectable. So I know that's kind of a fanciful example, but that's true, right? So we wouldn't be able to verify things like that. Sometimes people point out like moral truths, like Hitler was a terrible, morally terrible man. We can't verify that with evidence because those kind of moral judgments are based on, whatever our logic or our value judgments or whatever it is, or on philosophy. We can't verify that with evidence. We can't look at a microscope and say, oh yeah, Hitler really was bad. Let's get the telescope out. Let's do some test tubes and see. We can't do that. So that's what we mean by falsifiable. Physical and observable. So physical and observable means that it has to be something that's based in the universe. It's physical, part of the physical universe. Okay. So a good example of this is sometimes people talk about like we can't use science to verify like religious truths. Like if you imagine like God is outside of the universe, outside of nature, we can't use science to study something like that that's supernatural or whatever. Okay, so that's an example of what would be not physical and observable. All right, so enough on that. Make sure that when you come to test time, you have an idea about a question that is not answerable by science. Okay, so remember that was on lecture assignment 1. You should, and that's a short answer, possible short answer question. Make sure that you come to the test with a question that is not answerable by science. It's impossible to answer by science. Not, technically due to technological limitations, but theoretically, right? This is not the kind of question that science can answer. All right, enough on that. What's a hypothesis? What's the difference between a hypothesis, theory, predictions? Okay, hypotheses are explanations, a guess, kind of a educated guess about how the universe works. Okay, in the first lecture, I give that example of like the leaves falling off the trees. Okay, we could come up with an explanation for why that happens. Okay, the leaves fall off the trees because it gets cold during the season of winter, or maybe the daylight time changes. We get less daylight during the winter and the fall. That causes the trees to shed their leaves. Okay, so that's that's an example of a hypothesis. It has to be an explanation, trying to explain the cause. A lot of times hypotheses are causal. Okay, a lot of times they're causal. Trying to make this a little bit less thick. There we go. A lot of times they're causal. So they're saying this happens because of X. Okay, X happens because of Y. That's a hypothesis. Okay, a theory is kind of a higher level hypothesis. A theory, something becomes a hypothesis, becomes a theory once it garnishes a lot of evidence to support it. Before we have very much evidence to support a hypothesis, that's when we would call it a hypothesis. Okay, so it's kind of at this point an educated guess. It's still uncertain. Once we get a lot of evidence, then it gets bumped up to. That's to support it. We get enough evidence to support it. We bump it up to the level of a theory. Okay. Now, a prediction is totally different than a hypothesis, but people confuse these two things a lot. A prediction is a guess. I mean, you know what a prediction is, really. It's a guess at what's going to happen based on our hypothesis. So if our hypothesis is true, we expect to see X, okay? So if leaves fall off the trees in the wintertime because of cold weather, we expect that a tree that's kept kind of artificially warm in a greenhouse is not going to lose its leaves, okay? That would be a prediction at what's going to happen. Notice that predictions don't explain causes, okay? Okay, just answer what's going to happen. It's the crystal ball, right? You're trying to guess what's going to happen based off the hypothesis. All right, going on to global geography. What's the special name given to the 0-degree meridian? Remember, that's the equator. Okay. Do meridians intersect? They certainly do at both poles. Okay, both South Pole and the North Pole. Do the parallels intersect, right? So remember, if this is the Earth, here's the poles right here. There's north, there's south, right? All the meridians go from the North Pole to the South Pole, like so. Okay, the prime meridian goes through Greenwich. Now, you know that the parallels just go straight across like that, and they don't intersect at all. Okay, so parallels don't intersect, and that makes all the sense in the world because it's a parallel, right? Parallel lines don't intersect. That's the definition of being parallel. Which parallel is furthest from the poles? You can see the one that's furthest from the poles. Here are the poles here and there. One furthest from the poles is right here, smack dab in the middle, and that's the equator. Okay. So put equator. What is the climate like around 75 degrees south? Don't get too caught up on the number here. Okay. It might be better just to put high latitude or something. Don't get too caught up on the number. So, it's anything basically above, 66.5 degrees north or south. Okay, anything between that and 90, that's going to be high latitude. All right. So sometimes I have students on a test and they're like, "You said 75 on the study guide and it was 85 on the test." Well, it just means high latitude. Okay, so it's going to be cold there, right? That's the climate. Polar climate. Anything above 66.5 is polar. All right, what about 10 degrees north right here? Okay, again, don't get too wound up with this particular number because it could change on the test. This is going to be a low latitude, right? This is tropical, equatorial. Well, it's warm. Anything between, right, 23.5 north and south, anything between the tropical lines, it's going to be like that. Okay, it's going to be warm and tropical. What's the tilt of the rotational axis Earth relative to the ecliptic plane? That's 23.5 degrees. And you want to know that number precisely because that's one of those questions where I think you have to type in the answer. It's not multiple choice. Okay, so make sure you just know that answer. Now, the way number 10 is tested on the midterm is you're going to have, like, let's say you're going to have like A, B, C, D, E or whatever. And I'm going to say, like, which of these is Greenland? E in this case. Which of these is Japan? D. Okay. Which of these is... So anyway, you have to know everything that's on here. The Aleutian Islands are right here off the coast of Alaska. Okay. So that'd be Aleutian Islands. Japanese Island is right there, D. The Andes Mountains are basically right here, B. Okay. The Himalayas would be, I'm going to put the Himalayas, I'll put a H for Himalayas right there. Okay, that's the Himalayas right there, north of India. The Appalachians are here on the eastern side of our country, so I'll put a AP for Appalachians. The Rocky Mountains are basically, right here. So we'll put a R for Rockies. Gulf of Mexico, I hope you know where that is. I'll put a G for Gulf of Mexico down there where we live. That's Hudson Bay right there in Canada. Greenland is E right here. Iceland is this island right here, okay, off the coast of Greenland or close to Greenland. Sumatra is actually over here. In Indonesia, it's one of the Indonesian islands. The Philippines are here, okay, and so I'll put a PH for Philippines. And Lake Baikal is here at C, okay, right there in the kind of the middle of Siberia, Mongolia. Sahara Desert is, I'll put SD for Sahara Desert right there in North Africa. And the Atacama Desert, again, is really close to the Andes. It's on the other side, on the east side of the Andes. And that's, I'll put an AT for Atacama, okay? All right, going on to the metric system, again, you should know all 7 independent dimensions of measurement and their base units, okay? So I guess this is kind of stupid. This is supposed to be up with this stuff, but whatever. Made a little mistake there. But anyway, those 7 independent dimensions of the universe that you can measure are time, mass, distance, charge, like electrical charge, amount, luminosity, temperature. And what am I missing? Is that 1, 2, 3, 4, 5, 6, 7? Okay. Time is seconds. Mass is kilograms. Distance is meters. Charge is in amps. Okay, capital A. Amount of a substance is in moles. Luminosity is in candelas. And then temperature is in Kelvin. And a lot of times we use degrees Celsius too. Okay. All right. You should also know some of the basic metric prefixes, how to convert them between metric units. Okay, so you will have to do a little bit of that on the test, not too much. Basically know that we have our base unit, and then from the base unit, I'm going to give myself a little bit more space here. Let me kind of do this over so I have more room. Okay, boom, 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 boom. Okay, then this and this. Okay, so we have a base unit. So let's say like a meter, okay? And then we can go up by units of 10. So 10, 100, 1,000. You don't need to know anything beyond 1,000. So 1,000 is a kilo. So 1,000 meters a kilometer. 100 meters would be a hectometer. And then the next one would be a deca. Okay, decameter. So decameter is 10 meters, okay? Base units. If you scale down the base unit by 10, so now you divide it by 10, then you're going to be a deci, and then a centa. That's 1 over 100. And then you're going to be a milli. And that's 1 over 1,000. Okay? So that's how all that works. And you have to know how to do something kind of basic, like, for example, how many millimeters are in the base unit. So how many millimeters are in a meter? Okay, well, you go up 1, 2, 3, okay, from milli to centa to deci to base. That's 3 jumps. Therefore, you're going to go from 1 millimeter, because you're going up the ladder. So you're going to go to the right. So go 1, 2, 3, and you see that there are 1,000 millimeters in a meter. Okay, maybe that even just intuitively makes sense to you without even having to do the jumps. Okay, I don't think that you have. If you have any. I don't think you have any English system to metric system conversions to do on the test, okay? So I think it's just, boom, that. It's just moving the decimal point, okay? So just in the out of time constraints, I'm going to move on. If you want more examples of how to do that, I would say go back to the lecture number 2 and rewatch that part, because I go through like step by step a lot of processes to show you how to do those metric to metric conversions. Okay. All right. So going on to the basic Earth structure, how old is the Earth? Right. It's 4.5 GA. That's billion years old. Okay. That's yet another number you might have to actually type in. So make sure you know that number. It'll ask you how many billions of years old is Earth. You're going to put 4.5. Okay. What's the 4 basic layers or spheres of the Earth? Okay. So we have the crust, right? That's the outermost skin. Then we have the mantle. Okay. So I'm going to put there M for mantle. Then we have the outer core and the inner core. Okay. So that's kind of basically pretty proportional. Mantle's the biggest, by far the biggest part of it. Remember, the crust is made of rock. The mantle's rock, solid rock, okay? Solid. Both these are solid. Outer core is liquid iron. And the inner core is solid iron. Okay, so the only sphere that's liquid is the outer core, and that creates the magnetic field. Okay, what are the 4 basic layers or spheres of the Earth? We did that. Which of those layers are molten? It's the outer core. I'll put OC there for outer core. What are the 4 most abundant elements in the whole Earth? Okay, so those 4 most abundant elements, number 1 is iron, and all that iron is, of course, in the core. Okay, number 2 is silicon, magnesium, and oxygen. Okay, so those are the 4 most abundant that you should know. But in the Earth's crust, when we zoom in and look just at the crust, which is the outermost skin, that changes a little bit. Silicon and oxygen are at the top, followed by aluminum, and then iron is number 4. Okay, so basically it's the same 4 group of elements, except that you switch out for the whole Earth and the crust. You're just switching out magnesium for aluminum. Okay, now what's the composition of the core? The core is made of, again, iron, and that's Fe. By the way, be careful, because sometimes I use periodic table elements, okay, symbols in the test. So make sure that you know the symbols for all these things. Okay, so I wrote everything in terms of symbols here. So you should know those periodic element symbols. Be careful, because a lot of times people think iron is IR. That's iridium. It's not iron. Okay, iron uses the Latin form ferrum, which is Fe. Okay, so IR, get rid of that. What proportion of Earth's mass is in the mantle? So Earth's mass is, Earth is majority mantle. It's 66% mantle. The crust is only less than 1%. It's not even 1. Okay, so this is 66%, or another way is 2/3. The crust is 1% or less, actually, and the core is 33%. Okay, again, those might be numbers that you need to memorize exactly, because those might be numbers that you actually have to type in exactly. Okay, so be sure you know that. What's the dominant rock on the ocean floor? It's basalt. Okay, remember, that is a mafic volcanic rock. What are the 4 differences between continental and oceanic crust? Now, this is a short answer, so I'm going to put SA, short answer here, okay? You'll put SHA. So you definitely know this, and this comes up on the final exam too, so just this is really, really important, so make sure you know this. Oceanic crust, average density. Oceanic crust is going to be about 5 kilometers. Continental crust is going to be about 30 kilometers. Average, oh, I'm sorry, that's density. That goes down there. Blah, sorry. Density is 3 grams per cc here for the ocean, 2.7 grams per cc for the continental crust. Average age, oceanic crust is really only about 50 million years old, and probably that's average, and then the greatest age, the oldest, is only 180, so it's less than it's everything is less than 180 million years old. Okay, for continental crust, though, the average age is 2.5 billion years, okay, 2.5 billion. So that's a lot older. And the oldest is 4 billion, okay, giga-annum, 4 billion. Rock types, ocean crust is basalt, okay, but the continental crust on average is diorite. That's an intermediate igneous rock. Composition, composition here is mafic. The composition here is intermediate. Average elevation, ocean crust is -4 kilometers below sea level. Here it's about 500 meters above sea level. Okay. All right, so what's the primary difference between mantle asthenosphere and mantle lithosphere? The difference is mechanical. Okay. Think again of the difference between the things as cookies and cookie dough. Okay. Mantle asthenosphere is the cookie dough, and lithosphere is the cookie, the baked cookie. You know that cookie dough, you can squish it, you can mold it, you can bend it, but it's still a solid, okay? Lithosphere is not like that. So the asthenosphere is the cookie dough. The lithosphere is like the baked cookie. If you try to bend a cookie, what's it going to do? Crack, and you have crumbs, okay? And that's the same thing with the lithosphere. It's a mechanical difference. Is the asthenosphere warmer than the lithosphere? Yes. But that's an accidental difference. It's like a coincidental difference. It's a difference, but the real main, primary, essential difference between them is it's mechanical, okay? Minerals. Let's go into minerals. What are the 3 fundamental subatomic particles? List their charges and their masses. So for this one, 3 fundamental subatomic particles are electrons, protons, and neutrons. Okay? Charges, electrons are negative, protons are positive, neutrons are neutral, 0. Okay? Their masses, neutrons are 1 AMU, 1 atomic mass unit, protons are 1 AMU, 1 atomic mass unit, electrons are 0.0005 AMU. Okay, so they're very small. Much, much smaller than a proton. Okay. Okay, so now number 24. Where's the vast majority of an atom's mass concentrated? It's concentrated in the nucleus. Okay, so remember you have the nucleus, you have the protons and neutrons there, the p and the n's, okay? And then you have electrons orbiting in shells that are around the nucleus, okay? So you're going to have the negative electrons orbiting out here, okay? All right, now what's an ion? An ion is just an atom with a charge, okay? It just has a charge imbalance, so it's either positive or negative. If it's positive, we call it a cation. If it's negative, we call it an anion. Okay. I'm going to scratch out metallic bonds. We never talked about that. Ionic bonds are bonds that between ions. Okay, they're based on electrostatic attraction. Okay, so the fact that one is positive, the other's negative, and it's like a magnet. They stick together because opposites attract when it comes to electromagnetic charges. Okay, covalent bonds are bonds that involve the sharing of electrons. Remember that atoms are always going to bond on the basis of the octet rule. Okay, that means that they're going to want those completely full outermost shells, outermost valence shells. Now, that full outer shell, so that's going to make the atom very stable. So it's always trying to get to that full outer shell state. So it either does that by trading electrons, like I give some to my friend over here because they need electrons and I have too many to get an outer, full outer shell, or they're going to do it on the basis of sharing those outermost electrons so that everybody has 8 in their outermost shell, okay, and they're shared. All right, now know the criteria for being a mineral. There are 5 criteria. So first one is solid. Has to be a solid, no liquid minerals, no liquid crystals. Number 2 has to be formed by some kind of geologic process. So biological processes don't count. So example, your teeth, right, are made by a biologic process. So we don't count that as a mineral, okay, even though you know that your teeth are made of a mineralized kind of substance. Actually, it's called apatite, which is kind of ironic, I guess. But anyway, they also have to be naturally made. So it has to be natural. They have to occur somewhere in nature. They have to be crystalline. What does that mean? That means that every atom in the structure kind of has a place. Okay, it's highly organized. So all of the atoms occur in these kind of like rank file. That's a crystal structure, okay, rather than just being all jumbled up, okay? Number 5 is that minerals have to have a definite mineral formula. Okay, so I'm going to put here mineral formula, a chemical formula. Okay, so for example, quartz is SiO2. It's never SiO3. If it's SiO3, it's not quartz. It's something else. Okay, just think of minerals as they're like super uptight. They have to be just like everything is just right. Okay, every atom is in its place. There's a place for every atom. Silicon goes there. It's never anything else. Oxygen goes here. It's never anything else. I don't allow. They're super uptight. They want everything just so. Okay, so that's a mineral. You should know the chemical formula for quartz and calcite. Okay, SiO2 for quartz. Calcite is calcium carbonate, CaCO3. Okay, 5 most common minerals in the crust. So you should know those really common like rock-forming minerals. So feldspar, number 1. That's the most common one. Quartz. Okay, and then after that you have things like mica, pyroxene, olivine. Okay, amphibole. There's other things too that are common you should be aware of. Calcite, clay minerals, and also hematite. Okay, that's iron oxide, Fe2O3. All right, CaCO3 for calcite. Okay, so just make sure that you know some of those. I know I only asked for 5 there, but it's good to just kind of have some familiarity with these. Feldspar, quartz, mica, pyroxene, olivine, amphibole. These are not clay. These are silicates. Okay, that means they contain the silicate molecule. Okay, difference between silicate minerals, non-silicate minerals, right? Silicate minerals have that silicate molecule in them. It kind of looks like this, right? It's like a tetrahedron. Silicon on the inside, and there's 4 surrounded by 4 oxygens in kind of that pyramid type pattern. Non-silicates don't have silicate in them. So what's an example of a non-silicate? Calcite. Okay, hematite. That's that red iron oxide, right? Fe2O3. Clay minerals are silicates, though. Okay, so there's some examples. Some economic uses. Just make sure that when you come into the test, this I think is a short answer one. Just make sure that you know like 3 examples of minerals and their use, like their economic use. Okay, there's so many things I go over in the lecture, but quartz is used for glass. Graphite is used for pencil lead writing, but also for like lubricate. It actually has a lot of uses. It uses for insulation. They use it for also for lubrication of locks, for example. You often lubricate it with graphite. It's a good lubricant. What about uraninite, right? UO2. That's used for getting uranium for energy, right? Nuclear energy. What about hematite, Fe2O3? That's used as an ore for steel. Okay. What about galena, PBS? That's used as an ore for lead. So there's a lot of things. Go back to the lecture and just make sure you come into the test knowing 3 examples of that. I think it only asks for 3. Okay. Another question I see isn't on here, but I kind of want to add this on here is I think this is on the test and it's not on here, so I'm a little bit concerned about that. But there's also know some examples of minerals that are bad for your health, okay? Hazardous to health. Okay? Some examples of that are asbestos, mercury, okay? Silica dust can be very hazardous to your health, okay? So just come in knowing at least one example of a mineral. This is actually from your book. It's described in your book. Minerals that are bad for your health, okay? All right, going on to rocks, igneous rocks, sedimentary rocks. It's kind of a lot to unpack here, so we'll go through this as quickly as we can. Three major rock types, okay? Three major rock types are, right, igneous, sedimentary, and metamorphic. We don't really talk about metamorphic in this class, but we do talk about igneous and sedimentary. All right, for igneous rocks, make sure that you know the difference between felsic and mafic, okay? Igneous rocks we classify on the basis of composition. Okay, that's what it's made out of, elements of the periodic table, what it's made out of, okay? Felsic rocks are more Si, more that silicate. Mafic rocks are less silica, okay? Less SiO4, okay? Now, you also have, in felsic rocks, more sodium, more potassium. Mafic rocks have more, as the name implies, mafic. That Ma is for magnesium, the Fic is for ferric iron. Okay, so more Mg, more Fe. Okay, felsic rocks, felspar gives us the fel. Sic is for silica, so that has more SiO2 and it has more sodium and potassium, like I said. Difference between a plutonic intrusive igneous rock and a volcanic extrusive igneous rock. Okay, these are igneous rocks. Plutonic rocks form underground. They never erupt, so they form like in a magma chamber. Whereas, so these are things like granite, diorite, gabbro. Okay, so this is the magma chamber rock. So think magma. Okay, volcanic extrusive rocks form from volcanoes, right? So you have these rocks are the basalt, the andesite, the rhyolite, like that. Okay. For the following igneous rocks, you should know whether they're mafic or intermediate, felsic, and then whether they're extrusive or intrusive. So the best way to do this is set up, a table. Okay. Like that. This is going to be mafic. This is going to be intermediate. This is going to be felsic. And then these are going to be the intrusive and the extrusive. So volcanic. So mafic intrusive rock is a gabbro. An intrusive igneous rock, intermediate rock is a diorite. The felsic intrusive rock is a granite. Okay. An extrusive mafic rock is basalt. The intermediate extrusive rock is andesite. The felsic extrusive rock is a rhyolite. Okay, like that. So you should be able to kind of plot out a table like that and just memorize all those names. All right, so those are all the different kinds of igneous rocks that you need to know. There are a few more that are less important, but you should know a little bit about them. Obsidian, scoria, pumice. These are ones that are classified just off of texture. Obsidian is a glassy. It's based off of texture, so it's a glassy, volcanic glass. Okay. Scoria is a vesicular. It has lots of bubbles. And pumice has a pyroclastic texture. All right. So know the following igneous rock textures, or you say glassy, fine-grained, porphyritic, coarse-grained, and vesicular. So glassy means made of volcanic glass like obsidian. Porphyritic means that you have a fine-grained texture. Remember that fine-grained means you can't really see the crystals. I'm kind of drawing them really small, but really you can't even see the individual crystals. They're so small. But you have a few big chunkers in there. Okay, so that would be porphyritic. Fine-grained ground mass with a few big crystals in it. That's an igneous texture, and it's an extrusive texture that you get from a volcanic rock. Okay, fine-grained rocks, they're aphanitic. That means you cannot see individual crystals. Coarse-grained rocks are phaneritic. These are the magmatic rocks, the plutonic rocks, the intrusive rocks that form inside the earth from a magma chamber, cooling in the magma chamber. Then you have vesicular rocks. Those are ones with lots of vesicles, lots of holes. Those are erupted, extrusive volcanic rocks that had a lot of gas or maybe a lot of water in them. And all that water fizzling and fuzzing through create a lot of percolating through, create a lot of holes and vesicles in the rock texture. Okay, so volcanic igneous rock texture. All right, going on with a few questions from sedimentary rocks. Know the difference between a clastic, biochemical, chemical, organic sedimentary rocks. Clastic sedimentary rocks form from broken pieces of rock and mineral. Okay, they form from weathering. So weathered rock, okay, generates little pieces of rock and minerals. They come together and conglomerate together. They become a clastic rock. You should know at least some examples of clastic sedimentary rocks, biochemical sedimentary rocks, chemical sedimentary rocks, and organic sedimentary rocks. Okay, clastic sedimentary rocks would be, by the way, detrital is another word for clastic down here. Okay, those are things like sandstone, shale, siltstone, breccia, conglomerate. All of those are clastic. Gypsum and rock salt are chemical. Chert and limestones are biochemical. And organic rocks are coal or oil shale. Okay. Biochemical rocks form from marine animals. Okay, marine shells or planktonic creatures. They're tests. They're shells. So they're marine rocks. Okay, they form from shells. Chemical rocks form from precipitation. I'm going to put PPT for precipitation and evaporation. And you have just straight up mineral grains that form from a precipitated fluid. Okay, so you have water. Water, usually has dissolved mineral content. That mineral content comes out. It precipitates out. Okay, organic rocks have a lot of organic matter in them. Coal, oil shale. Those are the organic rocks. All right. So you should know these sedimentary rocks, whether, what category they are, chemical, biochemical, clastic. You should know a little bit about their mineralogical makeup, okay? Just in the most basic way. Clastic rocks are going to usually be composed of SiO2 silicate, okay? So clastic is usually going to be SiO2 silicate material. Biochemical rocks, on the other hand, are going to be mostly calcitic, calcite-based. Chemical rocks are going to be whatever chemical they are. Gypsum. Gypsum's made of gypsum. Okay, rock salt's made of halite. Okay, NaCl. Right. So things like that. And that's enough for the test. Diagenesis. Remember that diagenesis is the process by which you take loose sediment, sand, and silt and clay, the sediments, and you compact them together. You squeeze out the water leaves, and it's cemented together, or pressure solution basically fuses the rock grains together so that you have a compact, coherent rock, sedimentary rock that now sticks together. Okay, so it's the process, diagenesis, the process you take loose sediment and you compact it together and make it stick together to become a new coherent rock unit. Okay. All right, going on to weathering. So you should know the difference between chemical weathering and physical mechanical weathering. So chemical, this is a short answer question, okay? So make sure that you know you can explain this difference. Chemical weathering is going to be first of all, weathering. What is weathering? Weathering is breakup, destruction of rock, bedrock. So you're going to take the bedrock that's still part of the crust, attached to the crust, and you're going to turn it into a loose piece. Okay, that's sediment, creates sediment. Weathering creates sediment. How are you going to break it off? You can either break it off mechanically or chemically, okay? So when you do it chemically, you change composition. There's a chemical reaction, okay? With physical, there's no chem reaction. It's some physical process, mechanical process that just breaks the rock without changing its chemistry, okay? Now you should be able to give an example, at least one example of physical weathering and chemical weathering. In the lecture, I went over 3 different chemical weathering processes, okay? So chem, I talked about hydrolysis. I talked about carbonation. And I talked about oxidation. Right? For physical, I talked about 5 different things. Phys, mechanical. I talked about 5 different things. Thermal expansion. Frost wedging. That's where the water gets into a crack. It freezes, it expands, and it breaks the rock apart. I talked about joints. Those are cracks and faults that happen in the rock due to tectonic forces. I talked about exfoliation. That's when you have a plutonic rock that was originally formed deep underground, or a metamorphic rock that was formed deep underground. It's exhumed, it's brought to the surface by tectonic processes, and the pressure release cracks the rock, okay? Because when it's buried, it's under a lot of pressure. When it's brought to the surface, it's under very little pressure. So that pressure release cracks the rock. The rock expands and cracks, okay? I also talked about salt wedging. All right. That's when salt, in coastal environments, salt crystals start to grow in the cracks of rocks. They expand, they grow, the crystals grow little by little, and it cracks the rock to pieces. All right, you should be able to define, I don't know why mass movement is here. Erase that for right now. That's talked about down here, mass wasting. But you should be able to define weathering. Okay, we already did that. It's the breakup and destruction of the bedrock into smaller pieces. You should be familiar with various, again, belongs down there. So we'll talk about that in a minute. It belongs with mass wasting. Mass movement, mass wasting. Okay. You should know some biological weathering processes. We talked about root wedging. We talked in this class about organic acids. Remember with soils, how soils have that whole cation exchange capacity. Plant roots emit hydrogen ion, which is acid, to extract the cations from the rock and the sediment and the soils, okay? So that's a weathering process as well. We talked about lichens. Okay, so organic acids, I'll put up here cation exchange, CEC, cation exchange capacity, okay? You should also know something about how feldspar and granite breaks down through hydrolysis, okay? So hydrolysis is when water reacts with feldspar, okay, water plus feldspar, reacts and gives you clay minerals, okay? All right, going on to mass wasting, mass movement, and soils, okay? What are some rapid, and let's talk about these ones up here. So you should be familiar with some various mass wasting processes. That's basically talked about right here. We're going to talk about some of those different processes. Also, just be able to define mass wasting. Mass wasting is just the downhill movement of soil, clay, regolith, sediments under the force of gravity. Okay, so rock and regolith and soils and everything else is just moving downhill under the force of gravity. Okay, so force that drives it is gravity. What soil? Okay, we'll get to that in a minute. What are some rapid? So I just want you to come into the. This is a short answer question. So I want you to be able to come into the class and into the test. I mean, and be able to discuss a rapid mass wasting process, and also be able to discuss a slow mass wasting process. Okay. So for example, a slow one would be slumping. Soil creep. Okay, be able to explain one of those. I don't want to go, and I don't have time to go through all of those processes right now. Okay, but you should go back to the lecture and just make sure that you can say 1 or 2 sentences about slumping or soil creep or solifluction. Read the book, and there it explains each of those processes. But just be prepared to talk about one of them in a short answer format. Also be able to explain something about one of the fast mass wasting processes. Rock fall is probably the easiest one. Okay, rocks on a sheer face cliff fall under the force of gravity, directly fall without touching the ground, right? So until they hit the ground, right? They're not sliding, they're not flowing, they're just falling right off a sheer cliff face. That's probably the easiest one to remember. There are other ones: debris flows, earth flows. I don't really make that distinction in this class, but any kind of flow, debris or earth flow, and also debris slides I talk about as well. Just make sure that you come in, you can explain a a slow process and a fast mass wasting process in that short answer format. So make sure you can say 1 or 2 sentences about each one of those. Okay. What is soil texture? Why is it important? Soil texture is the Now, this is really important. People always get this screwed up with like rough or smooth. Rough and smooth has nothing to do with it. Get that idea out of your mind. Soil texture has everything to do with grain distribution. What does that mean? It means you have some ratio or some proportion of clay, silt, and sand. Okay? You have some mix of those. And that's what the texture is. The best texture is some combination of these that gives you loam. Now, why is it important? It's important because this is all important for soil fertility. Because different components affect the drainage of the soil, and also different components can affect the cation exchange capacity. Sand has a lower cation exchange capacity but better drainage. Clay has a very good cation exchange capacity, but it has very poor drainage. So there's kind of this give and take, and usually having a mixture of sand, silt, clay ends up giving you the best kind of soil fertility. All right. What are 5 factors that affect soil formation? So for soil formation, we have number 1 thing is time. It takes time to form a soil. Number 2 is the topography, right? Whether you have a really steep slope or a shallow plain, right? So if you have a steep slope, soil has a hard time forming on a steep slope because it gets washed down to the plain or the valley below. You also, you know that the climate's going to make a difference too. That's going to determine what kind of weathering rates, what kind of weathering happens, what kind of vegetation forms. Okay, and that's actually another thing. The kind of vegetation, how much vegetation, so the flora and the fauna, the life, the biological biosphere makes a difference here too. And the final thing here, what am I forgetting? I'm missing something here. What is it? Time, topography, climate, vegetation, and completely blanking. Maybe it'll come to me. Let me go check. Can't remember. Sorry, folks. Isn't that embarrassing? Can't remember. I'm forgetting something. I can't remember what it is. Here's soils. Soil. You probably know. I can't remember. I'm getting older. That's why. right here? Oh, of course, the parent material. So whatever the bedrock is made out of, right here, whatever the bedrock is made of, it's going to make a huge difference as well, okay? If it's made of limestone, it's going to be calcite rich, right? If it's made of granite, it's going to have a lot more feldspar in it. So it's going to have potassium and phosphorus and a lot of good nutrients and things like that. So whatever that bedrock material that provides the regolith is going to make a big difference too. Okay, so I'm going to put here parent material. Or maybe I could even put the bedrock. Okay, whatever the bedrock is. Sorry, I can't remember things like I used to. Getting older. Okay, on the sketch below of a meandering stream, label the cut bank, the point bar. So going on to streams, this is a diagram of meandering stream. Okay, so the inside of the meanders is where the water slows, and the outside of the meanders where it speeds up. So this is fast. Okay. So that fast water will erode this bank right here, and that'll be called the cut bank. Okay, so that's a cut bank, that's a cut bank, that's a cut bank. These, on the inside, the water slows down, and so it drops out its load, the stream load. So those create this buildup of like sand and gravel. We call those the point bars. Point bars, point bars, point bars. Okay. Over time, as the point bars grow, and the cut banks grow, basically what's going to happen over time is that these meanders are going to get more and more like this kind of a shape. They're going to get tighter and tighter and tighter. And eventually what's going to happen is maybe during a flood event, it's going to jump its bank. So the water's just going to jump, it's going to flow here, it's going to overrun its bank, and it's going to cut off this meander and create a oxbow lake. So it'll look like that, and then the new stream will just be straight, kind of going like this. Okay, then you have an oxbow. All right, you should understand the evolution of meandering streams. That's, what I just explained above. What's stream load? Stream load is all the stuff that's in the stream except for the H2O. Okay, so besides the water, there's lots of other stuff. Okay, that stuff is classified into three things. There's the bed load. That's the stuff on the channel bed that gets rolled along. The stream is rolling along boulders and sand often. There's the suspended load. Suspended load is the silt and the clay that makes the water look muddy, that gets suspended in the water column and carried along. And there's the dissolved. That's the invisible dissolved material that's in the water. Okay, you can't see it. The water will look completely clear. It'll look beautiful. You won't see anything, but it will affect the dissolved load. Will it's still carrying a lot of mineral material. It's dissolved into the water. Okay, that's what I'm trying to say. Okay, what are the three major zones of a river system? Okay, first you have the headwaters. Okay, so I'm going to put the head, and that's in kind of the mountainous elevated area. Okay, so that's where all these tributaries are going to flow out of the mountains, and we call this the zone of erosion. So this is where like the mountains are eroding away, and they're picking up all of the bed load, the suspended load, the dissolved load, and they're carrying that through tributaries into a trunk stream. So then once you get into the plains, you're going to go into the zone of transport and the trunk stream. So all that material is going to be transported downriver until it meets the ocean, in which case you're going to have a delta build up. And all of that stuff is going to get deposited into the ocean, and we call that the zone of deposition. Okay. All right, how does stream discharge typically change from the head to the mouth? Well, what happens is that as this stream flows towards the ocean, tributaries are constantly feeding into it. So the discharge, which is again the amount of water that flows through the stream per unit of time, is going to increase. Okay, and discharge, which is called Q, is equal to the volume of water per time, flows through time, and that's equal to the cross-sectional area, so I'm going to put area of the channel times the velocity. Okay, so those are things that kind of hydrologic factors that affect the discharge. What are some common flood hazard mitigation techniques? This is discussed a little bit in your book, although I have to kind of change this because I noticed in the new edition that we started just recently, they cut this section down a lot, so I kind of have to fiddle with this a bit. But basically, some flood hazard mitigation techniques are building artificial levees, dams, and there's also a technique which is discussed in your book called just natural floodplain management. Okay, so natural floodplain management means to just kind of assess the risk of a floodplain for hazards, for flooding hazards. And if it's an area that has a high propensity to flood, just don't build in that area. Let the stream do what it naturally does, which, flooding is not a, artificial occurrence, right? It occurs, it's a natural part of the evolution of a stream. Okay? So there's natural floodplain management. Just don't build in those areas. That's the bottom line. Dams help to control the amount of water that's flowing through a river over time. So what you can do is, if there's a lot of water coming through the river and it looks like it's going to overflow its banks, you can dam it up into a body of water, a lake or a reservoir, and let that water flow through at a more controlled rate, and that stops the river downstream from flooding. Of course, it can create problems upstream, but downstream, if there's a town or something like that, you want to stop it from flooding, you can control that better with a dam. Artificial levees are just kind of the most rudimentary way of preventing flooding. You're just building up the walls of the banks artificially with concrete and stopping, making the banks higher so it's harder for it to flood, okay? Another thing is also called channelization, in which you kind of do a similar process, but you dig out the channels and make them wider and deeper so they can handle more water, okay? Groundwater, you should understand porosity and permeability, okay? So porosity is how much pore space is available in the rock unit. Permeability is how well those pore spaces are interconnected. So porosity tells you how much water can fit into the aquifer, whereas permeability is how well that water can flow. Okay, so permeability allows water to move through the pore space of that rock. Okay, so you could have great porosity, but if the rock isn't permeable, it's useless as an aquifer because water can't move through the rock. All right. What kinds of rocks or sediment make good aquifers, which will make good aquicludes? First of all, let's be clear. What's an aquifer? What's an aquiclude? Okay. I have a question on the test where I show a picture of a rock, kind of close-up picture of a rock, and I say, which one of these is this going to make a good aquifer or aquiclude? A lot of students pick the wrong thing because they don't know what the difference between an aquifer and an aquiclude is. Aquifer means it has good porosity and permeability, and water can move through the rock, and it can hold water, it can move through the rock, and it can be used as a source of fresh water for human use. Aquiclude is the opposite, right? The water, it can't move through the rock. It's impermeable, and so that's oftentimes something like a clay stone, a metamorphic rock, a granite, something like that. It doesn't have very good pore space. Good aquifers would be something like a sandstone. Okay, sandstone typically has a lot of pore space and lets a lot of water move through the body of the rock. Okay. You should also be familiar with the following terms. Aquifer I just explained. Aquiclude I explained. The water table is the depth at which everything below, so I'm going to put WT, this is the water table. Everything below here is saturated. So the rocks below the water table are saturated with water. Above are unsaturated. Okay, so if you want to have a well, you have to make sure your well goes down. So let's say this is the surface. Okay, there's a little happy little tree, and there you are, and you want to dig a well. You have to make sure your well goes down into the water table. If it goes above the water table, you won't get any water. Okay. Artesian wells. Artesian wells are wells that are under natural hydraulic pressure, and they don't require pumping. The water will just flow out as soon as you tap the aquifer. Okay, so if this water just starts gushing out and you don't even need to pump, that's an artesian well. The cone of depression, that occurs when, let's say this guy's pumping water, and the water table will start to lower around the well because he's drawing out more water than is sustainable. So over time, the cone of depression will expand and the water table will lower. Okay, but it's a local depression in the water table surrounding a well. Subsidence is a problem that occurs commonly with groundwater where you draw out too much groundwater. The soils begin to compact, and the ground level actually begins to sink and get lower. The elevation of the surface gets lower. It starts sinking. It might sink unevenly, and it can create foundation problems and all sorts of problems for human use. Okay, for human society, I mean. All right. You should also know about the Ogallala Aquifer. It's located in the Great Plains. Okay. And it's a Pleistocene Ice Age aquifer. Okay, so it's very ancient, so over 14,000 years old. It's from, it resulted from the melting of the Laurentide ice sheet during the Ice Age. And it is a very useful aquifer for agriculture, and America's breadbasket is there in the Great Plains. But it's running dry due to over-irrigation. Okay, so too much irrigation. Too much artificial irrigation is sucking it dry, and it's being kind of treated in some areas as a infinite resource, and it's not. Also know some various features that can develop when groundwater flows through limestone. So you know that when groundwater flows through limestone, remember that water sucks up CO2, that forms carbonic acid, and that can drive carbonation. You all know about the carbonation. That's a really important process of weathering. You should know. Make sure you know carbonation. CO2 from the atmosphere dissolves into water, forms carbonic acid. The carbonic acid, in turn, melts away the limestone, dissolves away the limestone, because remember the limestone's made of calcite, and calcite reacts easily with acid. So then you end up with caves, caverns. Okay, you get sinking streams. Eventually, what happens is those caves and sinking streams cave in. You get sinkholes. They cave in, and then ultimately, as all the sinkholes combine and all the caves collapse, you end up with a final kind of landscape called karst. Okay. All right, what happens to carbon dioxide in the atmosphere when it reacts with water? So carbon dioxide, I already just explained this, gets sucked into the water. It dissolves into the water, it forms carbonic acid, and then that lowers the pH. All right, final thing, and then we're done. So what's a glacier? Glacier is land ice, and it's sufficiently massive to flow. Okay, so flowing is part of its definition. In order to get that big where it has enough mass to flow, it has to be able to accumulate every year, year in and year out. Okay. Next one here, you say you should know all the alpine glacial terminology, arêtes, what's this? Arêtes, cirques, and horns. So should probably be good if I could find actually like a diagram. I guess I could just draw it here for you, but boom, boom, boom. Let me do that. Okay, so after alpine glaciers have worked their magic, they've eroded the landscape, and let's say they've melted away, which has happened in this periodic way for the last 2 million years. With the cycles of glaciation, interglaciation, you've probably read about in your book. You end up with these horns. Okay, these are like very steep-sided mountains. They have very, very sharp peaks, horns. Okay, and there's these spurs, these kind of like sharp ridges that come off of the mountaintop, and we call these things the arêtes. Okay, and then in between the arêtes are these kind of bowl-shaped depressions, kind of like that. And these are the cirques. Okay. Like that. Okay, a lot of times arêtes hook up and you'll get another horn over here. And then there's another cirque. Okay, so that's what an alpine, sorry if this is a crummy picture, but this is supposed to be an alpine, glaciated landscape like that, okay? So these cirques used to have little what are called tributary glaciers that would have flowed into a valley glacier, a U-shaped valley, and a valley glacier system. So a lot of times there will be like a U-shaped valley next to these horns like this, and the tributary glaciers flowing into it, and you get these hanging valleys and things like that. Okay. So glacial terms such as zone of ablation, zone of accumulation. Again, let me kind of draw that out so I can explain it. When you have an alpine glacier, okay, so here's my mountain, okay. I'm going to draw a glacier on top. I'm trying to get need like a good ice color, so there's blue. Okay, so here's my glacier on top. And it starts flowing downhill, right? So there it goes, flowing downhill. Now, you know that once it gets so far downhill, it's going to start to ablate. Okay, it's going to start to evaporate away. Ablation just means evaporation. Okay, so this part where the glacier's gotten to such a low elevation that it can no longer maintain itself, right? It's melting away. It's not cold enough for it to be a glacier anymore, and be ice. It's going to start melting away and ablating away. Okay, we call that the zone of ablation, and then the zone of accumulation is happening up here where it's cold enough at this higher elevation that you're getting all this beautiful snowfall, okay, and the glacier is accumulating. It's getting larger, okay? So there's this mass balance where the glacial ice is moving downhill, it's being removed, and when it gets to the zone of ablation, and then it goes up into the atmosphere, and it becomes humidity, which then falls as snowfall in the zone of accumulation. So it's like a big treadmill. You should think of glaciers as just this big treadmill, this big cycle that's constantly eroding and destroying the landscape. Okay. All right, you should also know some of the examples of erosional and depositional features of glaciers. So let's kind of split these things up. So we'll have erosion over here, and we'll have deposition over here. Two of the depositional things we talked about, number one most important thing are moraines. Okay, moraines are the main depositional feature of glaciers. So those are the big winding hills of till that are left over at the terminus of a glacier. Okay, so the toe of the glacier. So if you go back up to this picture of a glacier, it's going to leave these piles of sediment, right? There's constantly sediment being picked up by the flow of the glacier and moved downhill into these very poorly sorted piles of till called moraines. Okay, it's just like a treadmill. Treadmill's constantly bringing material in and depositing it at the base of the treadmill. So that's the moraine. Okay, so there's moraines, but there's also outwash plains. Outwash plains are the areas at the base of the mountain, the plain or the valley at the base of the mountain, where all of the meltwater, again, every season, this is going to melt. The glacier is going to melt, and it's going to bring lots of streams of water, sediment-laden water, out to the outwash plain. It's going to deposit all this stuff in the outwash plain. Okay, so there's the outwash plain. Some other important terms to know are till. So moraines consist of till that's poorly sorted, deposited by ice. Another term is over here, outwash plain contains outwash. That makes sense, right? And it's all of the glacial material that was deposited by the stream water, not by the ice. Okay, so there's difference there. We also get glacial erratics. Okay, glacial erratics are the big hunks of rock, sometimes as big as a school bus. They're really large pieces, boulders that get deposited erratically around a glaciated area. Okay. As far as erosional features, we have Roche Montagne, which are these plucked up pieces of the bedrock. They get plucked up by the force of the glacial ice flowing over the bedrock, and they actually show the direction. They're like little hillocks, and they actually show the direction of the glacial flow. We also have glacial polish, right? That's where the sand and the silt and the clay that's ingrained into the flowing glacial ice polishes, just like sandpaper, polishes the bedrock beneath of it. And then we also have striations. Striations are where we have hunks of boulders or cobbles that are caught, ingrained into the flowing ice that scrape out these grooves in the direction of flow. You get these deep grooves called striations or scratch marks that are in the embedded into the bedrock. Okay. All right. You should also know some glacial difference between glacial drift, till, outwash. Drift is a general term to refer to both till and outwash. Okay. Glacial drift is just like any glacial sediment. Okay. It's an umbrella term. Whereas glacial outwash is the stuff deposited by the water. We talked about that above, the meltwater. And then the glacial till is the stuff deposited by the ice itself. Okay. So the moraines are made of till. The outwash plain is made of outwash. Make sure you know the two ice sheets on Earth right now. That's Antarctic and the Greenland. That's a kind of a fill-in-the-blank answer on the test where you actually have to type in the answer. Okay, so it won't be a multiple choice. Multiple choice would kind of be too obvious, right? But you have to know. You have to type that in. It's not a short answer. It's just kind of a fill-in-the-blank type of thing. You should also know a little bit about glaciation, interglacial, glacial periods in the Pleistocene, and what kind of caused those glacial cycles to occur. So if you read this in your book, it does talk about we're not exactly sure it's true. We're not exactly sure kind of what caused the onset of the glaciation. But what maintained it, these glacial cycles, is pretty clear. And those are called Milankovitch cycles. And what those refer to are changes. It's named after a Yugoslavian. I don't know if Yugoslavia is really not even really a country anymore, but a Yugoslavian scientist who talked about astronomer actually, who studied periodic changes to the tilt of our axis. Okay, so the tilt, how much tilt we have. Remember that it's 23.5, but it's actually been 24.5 or 22.5 over Earth's history. Okay, so it changes periodically like this. There's also something called precession, which is the wobble on our tilt, which goes like that, so it changes a little bit. And we also have something called eccentricity of our orbit. So that's where our orbit becomes more or less I'm trying to show this. So more or less circular over time or more elliptical over time. And that will cause all these things combine together to form, and they change on a periodic basis, and they all combine together to change the amount of solar radiation we receive from the sun. Okay, and that ends up creating this cycle. There's been 20 glacial interglacial periods over the last 2 million years. Okay, so if you do the math, that means about 100,000 years for a cycle to occur. So anyway, actually less than that, 10,000, I'm sorry. No, wait, no, 100,000. So anyway, that's how these cycles occur. Okay, so I think that's it. We've covered everything. And good luck studying for the test. Flashcards. Make flashcards of what you see there on the study guide. That's what I would really recommend to do well. And I just wish you good luck. Let me know if you have any questions. And I'm here to support you. So good luck on your test.